Okay, so I prepared some remarks about some things that you guys did, and that's what we'll do today. All right. Okay. So, yeah.
Homework 4 is also due Monday?
Yeah, homework 4 is also due Monday.
Oh, okay.
Yeah. So there's only 3 problems, right? I added 3 problems. I'm not going to add any more. I'm not adding any more.
Okay.
So you guys, I want you guys to do those, and then I want you to do the corrections. Okay? Okay. All right. So, general remarks. On the homework. Okay, so I think some of you use the internet, so that's okay. But you guys should cite your sources. Okay, so if you use something online, you know we're in a time where you guys have your cell phone and you have the internet available to you at all times. So why don't you just if you found something and you're using it, just say you're using it. Okay, so. Also, don't copy. So you guys, I saw that a lot of you guys worked together, and it was really easy to see who worked with who because there were some mistakes that propagated within your group. Okay, so you have to be very skeptical of the people you're working with. Okay, so make sure, don't trust them, right? So you should check the things for yourself. Okay. Make sure that you understand what's going on and don't just copy things down. Okay, does that make sense? All right. Other things about just mathematical writing. So use, when you start a proof, use the word proof. Underline it, put a colon there, and that lets me know when the statement stops and when the proof begins. Because sometimes you'll say, let this be blah, 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 and sometimes it looks like you're supposing the thing that you're trying to prove. And so if you write proof, it clears up where the proof is starting. Also, you could use QED or a box or your favorite symbol. You can make up a flower, put it at the end of your every single proof. But that also helps me know when you've finished a proof. Okay, so spacing is also good. The other thing is to state what you're trying to prove in words. In words and how you're going to prove it. So sometimes you'll start something by cases, right? But you'll just start into the cases. You'll just be like, suppose this, suppose this, suppose this. But before, if you just said, okay, we're going to break this up into cases. Here are the cases. Okay, now I'm going to prove the cases. And you say case 1, then start doing it. It's a lot more clear what's going on. Does that make sense? Just, more words, the better. Okay, that's really the end of the general remarks. Then I have some things about group theory, and I have some things about group theory, and then I have some things about special prime numbers, which is more of a fun topic. So these comments are about the relevance of the exercises that I gave. Okay, and then I'm going to talk about kind of things that you can't do with groups. So. Okay, so problem 4, so homework 3. So I graded the even ones, as you can see. So homework 3, number 4. So for group G, the following identities I guess, following facts. Okay, so the first one, or I guess I called it A, was that if you have, and maybe I used different letters. So if you have xy times xz, so when I do a times here, when I just write it like this is really the group operation. Okay, so I'm just using a shorthand here. This implies that y is equal to z. So this is one of the statements that we had. And so this is called left cancellation because I'm multiplying on the left by group elements, right? And then I can cancel it to get y is equal to z. Okay. The other thing that I have was that if y1 x is equal to e, so e is the identity of the group, and y2 x is equal to e, then y1 is equal to y2.
So we can't assume that when the letters are together that it's multiplication and therefore abelian, because what you're really
No, it's group multiplication. Yeah, you cannot assume that, and that it's not a, yeah, exactly. You cannot assume that it's abelian, right? They're not necessarily numbers. So this could represent like matrix multiplication, right? Or just like if you take strings, right, and you put two strings together, and you just take two like groups of strings and you concatenate them, right? This could be like a concatenation operation.
But it's not a multiplication because it's not like specifically stated that it's like.
It's not a multiplication within a ring, say, right? Where the ring multiplication is always commutative. Yeah. So that's a good question. No, it's not. Okay. So if you have something like a left identity and a right identity, then well, actually, I guess we had this. Y x is equal to e implies xy is equal to e. So left identities are also right identities. So this thing here, so here, y here, this is called the left identity. Or sorry, left inverse, not identity. Left inverse for x. So this is saying the left inverse for x is also a right inverse for x. Okay, and just to make things clear, I'm just saying here, x, y, y1, y2 are all elements of G in this statement, in these statements. Also, these y1s have nothing to do with, well, these, let's see, I guess these x's and these x's are not necessarily the same thing. Okay, so these are just kind of three independent statements. Okay, does that make sense? Okay, so let me tell you what the point of this exercise was. Okay, so the point of this exercise was to show x inverse is a thing. What do I mean by this, right? So like, so that there is the inverse, not a inverse, but the inverse of a given element of a group. Okay, so let me try and clarify this by saying what the axioms were. So originally, so this point is saying that so let me say for each. Okay, so the original axiom for inverses so we had the original axiom for group inverses. It said for all x in G, there exists a y in G such that yx is equal to the identity. So E is the identity of the group. So this is saying, so in class I wrote yx is equal to E and xy is equal to E. So that was one of the things I did. I said that I assumed it's commutative. I actually wanted to show you that you only need to assume this. Okay? This is the original axiom for inverses. And if you have that, so the point is that given, let me move this over a little bit. So what we proved can prove from the simplified axioms, like bare bones okay, so for all x an element of G, there exists a unique y an element of G such that xy is equal to E and yx is equal to E. Okay, so there's a unique, so for every one of these guys, there's an inverse, but it's also unique, right? The uniqueness statement is something like this here. So if you have that these two guys are the same, right, then, so if you have a left inverse for x and you have another left inverse for x, then you conclude that they're the same. So this is a uniqueness statement. Does that make sense? Okay, and it's like once we prove all these things, or once we can conclude this statement from a simple version of axioms, then, you know, for every x we can invent a new definition, right? And this new definition is the guy, the single element of G that satisfies these things and is unique. And if you multiply it on the left of x, you get the identity. And if you multiply it on the right of x, you get the identity. Yeah, does that make sense? Okay, so yeah, so this is the inverse of x. So this is this guy here. Is the inverse of x. Okay, all right. So that's what I wanted to say about that. So I want to talk about things that you can't do with groups. Okay. Okay, so I wrote down a list of things. So here, so this thing here, let's say y an element of G here, these things don't make sense. Okay, the only time plus makes sense is if your plus is your group operation. So, and this thing here needs to be defined. And maybe you could write this symbol instead of this thing. But I think a lot of you guys were thinking that you could just take an equation like this and subtract things to both sides. You can't do that. Groups only have one binary operation. They don't have a plus, they only have a times. Okay, and the times is some abstract operation. So like you couldn't just take this thing and move it over to one side. Right? So the groups aren't allowed to do that. So in general, does that make sense? So it's just kind of an abstract formalism where we don't have two operations anymore. We just have one single group multiplication.
Even if it's a group multiplication, we shouldn't use 1 over x, even though that implies like a times a negative, or an x to the negative 1.
Yeah, so you should, I mean, so unless you define what this symbol means, then you shouldn't really use it. But if you define the symbol to mean the unique guy such that this, then you can use it.
So
like
so what would be the symbol for
the inverse?
multiplying? Okay, so you just multiply by the inverse.
Yeah,
instead
yeah,
of
yeah.
having like a 1 over x.
Yeah.
Okay.
Yeah. So yeah.
So even if the group operation ends up being addition, you still can't subtract both sides. You start like x star something is still that.
If x star is addition, then you can subtract both sides. But you like do minus both sides. But that'd be like taking the inverse of both sides. So there is an operation here which is inversing something. So if you have an equation, what you can do is you can take the inverse of both sides, right? That would be like applying this -1 operation.
So it could So if the group operation is addition, you could have an additive inverse.
Yeah, if your group operation is addition, you have an additive inverse. But we just call it the group multiplication inverse in general.
Okay.
Yeah. Yeah. But we say additive only when the group is abelian, meaning it's commutative. Which brings me to my next point. In general, for general groups, like groups of matrices, xy is not equal to yx. Okay? And xy squared is not equal to x squared y squared. Right? You can't distribute like that. To write out xy squared, you actually have to write out what the word is in all together. So to write out what the word is, so we always have, if you wanted to square it, xy squared, this is just xy times xy, which is xy. Okay? So here, you just can't use these rules anymore. For example, like just because it's multiplication doesn't mean it's abelian. And let me also say that like this is the first time you guys are doing groups. Do not feel bad about this at all. Okay? This is like it's the first time you've seen a group, right? So like it's conceivable that people could think that, right? So I'm just telling you guys now, and then we fix it. You guys do the corrections. We go on our way. All right? Yeah. Why? Because so to show that that's true, we need to give an example of a group. So some set with this binary operation where this doesn't hold. And the example that I gave you was 2 by 2 matrices. So 2 by 2 matrices which are non-singular, which means its determinant is not 0. Yeah, so matrices are an example. So that's one of the examples that I gave in class. Yeah.
Yeah. So like, if we just assume like we always have xy times xy. You treated them as like matrices because it's like left multiplication. You'd have to first figure out what xy is and then work your way this way.
Yeah. Something like that. Yeah.
So that's why like x. That's why you can't rewrite it as x squared y squared.
Yeah. There's also, that's why you can't write it as x squared y. So there's also a group where we just work with symbols, right? So we work with words built out of the letters x and y. So it's like I can totally make this is called a free group, right? So this is a group I haven't told you about before. But there's groups where, well, OK, so I just take 2 generators, 2 elements, and then I build all the possible words out of them, like xy, xyx, x whatever. And then I also throw in inverses. And the only rule that I'm allowed to use is that x times x inverse is the identity. And the identity behaves as the identity is supposed to. So in this one, when you're just writing out words, because xy and yx appear in different places in alphabetical order, they're different elements of the group. Right? So they're just lists of letters. Right? Does that make sense? Okay. Okay. So how can we manipulate equations? So let me talk a little bit about what you can and can't do with manipulating equations. So given an equation in a group, like z is equal to w, right? So these are 2 elements of the group. Suppose I know that they're equal. Okay. So you may multiply both sides on the left by a single element, on the left by an element, or on the right. By a single element, right? But you can't mix. So let me tell you what I mean. So what's OK? So let me show you things that are OK. And then I'll do things that are not OK. OK? So here, if you have z is equal to w, this implies xz is equal to xw. Or you could do z is equal to w implies zx is equal to wx. So here I multiplied both sides on the left by x, and here I multiplied both sides on the right by x. Does that make sense? Okay, what you can't do is z equal to w implies that xz is equal to wz. So this is not okay. This is bad. Right? This is not a thing. Right? Wx. So here I multiplied on the left by x, and here I multiplied on the right by x. Does that make sense? So you have to do the operation, the same operation to both sides. Okay? And left multiplication and right multiplication are not the same operation. Yeah?
Sorry to go back to xy cannot equal yx. I'm just kind of curious. So like, going back to matrices, you have a case where like xy exists, but yx might not exist if the matrices are like a certain size, right?
Yeah, so here, when the example of matrices, right, so for the example of matrices, you always have to deal with special matrices. And for them to be a group, they always have to have an n by n. They have to have the same size, right? And then they have to have a matrix inverse, right? So they have to be, 2 by 2, right? Or 3 by, so 2 by 2 matrices and 3 by 3 matrices, they're not in the same group, okay? But 2 by 2 matrices where the determinant is 1, meaning that, and that's equivalent to the condition that there is a matrix inverse, right? That would be a group. So you don't multiply like a 2 by 3 matrix times a 3 by 2 matrix. So those don't have inverses in general, right? You need an identity matrix, and the identity matrix is, you have to have left identity, right identity type thing. So that one has to be this like diagonal matrix with ones on all the sides, okay? The good example to think about is just like letters, right? I think that's a really good one to think about. Is just think about like, you just make bunches of, you pick your 2 favorite letters, right? And then you make all the possible words out of those letters and the letters with the inverse involved. And the only rule that you're allowed to do is collapse when x and x inverse are next to each other, right? And so that makes a group, okay? All right. Okay, so any questions on that stuff, on these just like things? I think when you go back and look at what you guys were doing, I think it'll make a little bit more sense, these comments. And then you can go back and look at the video too. All right. Cool. All right, so I'm going to do something a little more fun now. I want to talk about another one of the problems, so again, the point of that problem that I did was to show that the inverse of an element exists. It's a left inverse and right inverse, and it's unique. Okay, so, and the point is that from the weaker axioms that we can derive some stronger consequences that are useful. Okay, so now I want to talk about some special prime numbers, which is more fun and relates to the last problem on the homework. Okay, so okay, so from homework work 3, number 6, and so we showed that if a to the n minus 1 is prime, then, so a and n are natural numbers, okay? If this is prime, then a is equal to 2, or sorry, a is equal to 2, yeah, and n is prime, right? So if this whole thing is prime, then the exponent here has to be prime. Does that make sense? Okay, so this was what we showed. And the trick, and I think a lot of you guys got this trick, was to use a geometric series, or geometric sum formula. Right? So we factor an a minus 1 off of this thing. Okay, so there was, let me just make a little remark over here before I continue with this. So there's a big no-no that you guys did. So, So let me just say what you guys did. So you guys said something like, since x divides y, this implies x minus 1 divides y minus 1. Okay? So this was something that you guys said, right? So, so this is not true at all. So this is one of the reasons, like I saw a lot of you guys write this, and that means that a lot of you guys were working together, right? So this is not a thing, okay? This is not cool, okay? So let's look at this. So like, I think 4 divides 24. Okay, this is true. Right, 6 times 4 is 24. Again, this is not like a division symbol. Okay, this returns true or false. It doesn't return a number. It's not a fraction. It's a relation. Okay, so this thing is this, and then so we do 3 divides 23. That would mean this thing. So this is x minus 1, and that is y minus 1. This is not true at all. Right? So this thing is bogus. Okay, so you can't do that. Right? Just because you have a relation here doesn't mean that you can like manipulate both sides of this relation and it'll be preserved. Okay. All right, I just wanted to say that. Okay, back to this fun thing. Okay, so so we had this thing. So okay, so let me give you a definition now. So definition. Okay, this thing gives a necessary condition for a to the n minus 1 to be prime. It's necessary for a to be 2 and n to be prime. Does that make sense? So that's why I say it's necessary. And we give a definition to primes of this form. Okay, so a prime of the form 2 to the p minus 1 is called a Mersenne prime. Okay, so this is one of the things that I had you guys show. I had you show that if we're going to look for special primes, right? One of the special types of primes are called Mersenne primes. All right. So Mersenne primes they look like this. And let's write out the first couple of Mersenne primes. Let's make a little table here. So okay, so MP will be 2 to the p minus 1. Okay, so let's do it like this. We'll do p. Okay, so 2 to the 2 minus 1. So that's 3. Okay, we have to do the next prime number. So 2 to the 3 minus 1, that's 7. Okay, 5. 2 to the 5 minus 1. Okay, so 2 to the 4 is 16. Okay, and so the next one's 32. And so this is 31. Okay, 31's a prime. Okay, so 7, so 2 to the 7 minus 1. Okay, so 32, 64, 128, and I think the next one's 127, right? So 127 is the next one. All right, so this keeps going, and then we can go, so this is, this is M2, M3, M5, M7, okay? And if we go to the next one, 11, so 2 to the 11 minus 1, so this number is, well, so that doesn't seem right. So 250. So okay. So this is. Let me see if this is correct. Well, I'm not sure if this is correct. I might have to make a correction in the video. This is what I wrote down. So what's 2 to the 11, guys? 2 to the 11. So I guess this is saying that 2 to the 11 is 2048. Is 2048 power 2? Yeah. Okay. So. Okay, so then maybe this makes sense. So this is what I wrote down, and this one is the first one that's not prime. Okay, so this is M11. But it turns out that you can keep doing this. Although this one's not prime, there's many after this that turn out to be prime. And this is one way that people build really, really big prime numbers. And really big prime numbers tend to be of interest for actual applications of cryptography and things like this. So I'm not actually sure if they use Mersenne primes, but certainly large prime numbers are used in things like RSA encryption, things like this. Okay, so these are the Mersenne primes. Okay.
Why is
For where here? So we're only plugging in prime numbers.
Oh,
So we only plug in the prime numbers. So we're taking primes to get new primes. Yeah. Okay. Okay. So there's another collection of primes that are called Fermat primes. So in homework, or sorry, in handout 2, what was the number here? Section 1, number 9. Section 1, number 9. So what did we? So the statement is, it shows that if A and N are natural numbers, and A to the n plus 1 is prime, then A is even, and n is a power of 2. Okay, so here again we're working with natural numbers. Okay, so this is the proof of this is actually quite similar to this one. It's a geometric sum trick. All right, and now I'm going to give you a new definition. Okay, that's similar to this other thing. So definition. So a Fermat prime is a prime of the form so 2 to the 2 to the k plus 1. Okay, so these are Fermat primes. Okay, so we have Mersenne primes, and now we have Fermat primes. And this comes from this necessary condition. Here we took A to be 2, right? But in general, it said that A could be even from this statement here. Okay, so let's write out what they are. Yeah.
Where did 2329 come from? What was that?
So here, I'm showing that it's not prime.
Oh,
So that came from, so these here are all prime numbers. And the question you can ask is are there infinitely many Mersenne primes, right? Another question you can ask is, are there infinitely many Fermat primes? And let me just tell you what the answers are, right? They think that there are infinitely many of these, but it's open problem, completely open. So if you prove this, you'll be famous, okay? That there are infinitely many Mersenne primes. Similarly, there's Fermat primes that look like this, okay? So let me write out the table here. And that's conjectured that there's only finitely many of them. So let me write out the table for Fermat primes. Well, let's do it over here. So Fermat primes. So this is the same Fermat from Fermat's last theorem, and the same Fermat who invented the derivative. Okay? So here, we could have, let's say, k, and then we could have fk, which is 2 to the 2 to the k plus 1. Okay, so you could just go 0, 1, 2, 3, 4, 5. Okay? We'll just do the first couple ones of these. So this is 2 to the 2 to the 0 plus 1. So this is 2 to the 1, so this is 3. Okay? So now we do 2 to the 2 to the 1 plus 1. So this is 4 plus 1. This is 5. Right. No, k's here are integers, right? P's are primes. P's a prime. Yeah, that's a pretty common thing.
We're just trying to get a prime.
Yeah, we're trying to get a so the thing was, so what was the point? The point was we had these conditions, right? So we had this a to the n minus 1 and a to the n plus 1. Okay, it was necessary for them to have a certain shape in order for them to be prime. That's what we could prove. right? And now we're wondering, okay, well, now I can try plugging in a couple numbers and see if they actually are prime, okay? So if it's necessary for them to have a certain shape to be prime, and now we can like check and see if they are. And it turns out when we plug in the first couple numbers in both these examples, right, we get lots of primes, right? So here, I'm going to do the same thing. So f2, so this is 2 to the 2 plus 1. So this is 2 to the 4, right? So 2 to the 4 is 16 plus 1, which is 17. Okay, so 2 to the 8 plus 1. Okay, so that's 256 plus 1, and that's 257. Okay, and 2 to the, okay, so now we have 2 to the 4. So that's 2 to the 16 plus 1. So this number ends up being this. Okay, and all these numbers here, these are the first 5 Fermat primes. So these are all primes. And then what happens again is it breaks. Okay, so this one breaks again at 2 to the 5 plus 1. And you just get some like monstrous number here. But this ends up being 64 times, this number here, 00417. Okay, so these are zeros here. Okay, so this one actually factors here. Okay, and so here are the conjectures. Right? So again, these are the open problems that I think maybe you guys will find interesting. Conjectures. So the first conjecture is there are infinitely many primes p such that 2 to the p minus 1 is prime. Okay, so that's an open problem. So if you solve that, that's kind of a really famous math problem. It's really old. Okay, and the other conjecture is that there are finitely many Fermat primes. So people have kept their computers on for years, and it stops there. Right? So after this, they've been able to factor all the other ones. Well, I'm not sure how big they've been able to compute, but yeah, so they can't. These are the only Fermat primes that we know of. All right? But we can't. There's no proof. Right? We don't have a proof of this fact. We don't have a proof that this one always works. It's a really strange thing, too, if you think about it, because if you do so what did we do? We did a to the n plus 1, right? We asked what happens when it's prime. And then we did a to the n minus 1, and we asked what happens if it's prime, right? And you're led to 2 different things, which have totally different behavior, right? And which we can't prove anything about. But the interesting part about all this is that you guys have kind of reached a milestone, and that you can prove your first non-trivial facts about number theory now, right? And now you can actually, so what we've done so far is we've done things where we've gotten to a point where we can actually show these necessary conditions about these numbers, right? About prime numbers, which I think is pretty cool, right? So I think that's something you guys should be proud of, right? Okay, so, and it's fun. Okay, so where are we now? That's what I had to say about these 2 things. All right. So I have, so next time we're going to talk about mathematical induction. But now I want to do some more exercises with you guys. Okay, so here's what I want to do. So we're going to stop for today, right? And then we're going to do some exercises. Okay, so we're going to do handout 2, section 6, or we can do handout 2, this other problem, which was the one that you guys started. I'll show that like x squared minus y squared is equal to 10. Has no solutions with x, y, and the elements of the natural numbers. Okay? So these are the two things that I want you guys to work on. So these ones are fun. I think these ones, this is like this example, counterexample thing. And I think you guys will enjoy that. So it's kind of like puzzles, right? All right.